Those cycloalkanes. Cyclo should make us think of circles. Cycloalkanes have at least one ring of carbon atoms, and we kind of mentioned these before. So this is cyclohexane. 6 carbons, and all 6 of those carbons are in the ring. So we have 6 carbons playing Ring Around the Rosie. And we have enough hydrogens to satisfy the 4-bond requirement for each carbon. So they're going to have 2 hydrogens each around the outside. When we draw the line structure, it's a hexagon. So we understand that the hydrogens are there. We name these guys by looking at the number of carbons that are in the ring and using the same prefixes as we did for the straight acyclic alkanes, and we put this prefix cyclo in front of it. So here this has 4 carbons. 4 carbons is butane. They're in a ring, it's cyclobutane. This has got 8 carbons in a ring, it's cyclooctane. They're giving boiling points here. I just want to point out the trend is to higher and higher boiling points. As the molecules get larger, the strength of the intermolecular forces becomes larger and the boiling point gets higher because it takes more heat to give those molecules enough energy to boil. We name the substituents in the same way. If we have more than one substituent, we need a number. But if we only have one, we're fine. When we have more than one, we sometimes have to decide where we're going to start numbering because you could start at either one. And so whichever one gets the alphabetical priority, the lowest in the we say the highest alphabetical priority. It's got the highest priority. It comes first in the alphabet. That's the one we're going to choose for number 1. And then you can number clockwise or counterclockwise, but we're going to number to give, again, the lowest numbers. So here we're looking at this ring. There's 5. That makes it cyclopentane, and there's a methyl group on it. We're just going to call this methyl cyclopentane. We're not going to put a 1 in front of it, because no matter what we do, there's only one of those guys, and the methyl group is always on the first carbon. Since it's always on the first carbon, we're not going to write it. But we're trying to be concise and not write extra stuff, is maybe one way to think of it. Or maybe this is another example of the bias the chemists have against the number 1. Here we have 2 methyl groups on the cyclopentane. So this is dimethyl cyclopentane. And one of these is going to be number 1. And if we number this way 1, 2, we get 1, 2 dimethyl cyclopentane. If we were to number the other way, we'd end up with 1, 5. And we don't want to do that because that's higher numbers. These 2 are identical, and so you could call either of them number 1. It doesn't matter. Here's another cyclopentane. Here we have 2 different groups, though. We have methyl and we have ethyl. And now we have to use the alphabetical priority. So there's methyl and ethyl. So you look at their names and say, which comes first in the alphabet? Well, ethyl does. So ethyl gets to be number 1. Then we're going to number either clockwise or counterclockwise to give the lowest possible number to the other substituent. So in this case, we're numbering counterclockwise, and so this is number 1, that's number 2. So 1 ethyl, 2 methyl cyclopentane. Yes?
Is the acronym that you gave us, so is that the only thing that requires the alphabetical order, or do you also, like, if there was like chloro there?
Yeah, if you had chloro in there, you would consider that in the alphabetical order. If this had a chlorine group on it, chloro, Chloro comes before ethyl, and so that would be number 1. These rules seem kind of weird at first. Once you learn them a little better, there is reason behind them. And they're trying to the goal was to have a fairly concise way of naming things that everybody could agree on and where we would get one name, only one name for any given compound. When you get into the really, really complicated ones, even old organic chemists sometimes argue about what the name is and which rule takes preference, and they great delight in that. Any other questions? So let's try some. Give the IUPAC names for these guys. So that first one, what's the base name? Cyclopentane. 5 carbons. And what is the name of the group that's on it? 2 carbons is ethyl. So we put the name of the substituent in front of the name of the longest chain. Does it need a number? No, it doesn't, because there's only one substituent, so it's obviously going to be on number 1. Okay, let's look at the second one. This guy. That almost looks like a fish or something, doesn't it? Some of these, you can draw some molecules that make some pretty funny pictures. But the ring here has how many carbons? 3. So that would be cyclo what? Mom eats pickled propane. Cyclopropane. What are the groups on the cyclopropane? It's going to be dichloro because there's 2 of them. So dichloro. Remember, chlorine has an H in it. I don't know why, but it does. Does this need a number? It does, actually, because it would be different if this chlorine was on a different carbon. That would be a different molecule. We need to specify that both of these chlorines are in the same carbon atom. So it's going to be 1,1-dichloropropane. And that's this guy. How about the box thing over here? What's the name of the box? 4 carbons. Cyclobutane. And then the 2 groups are bromo and methyl. Which one gets priority because of the alphabet? Bromo. So then when we number this ring, that has to be number 1. Then the direction we number is going to depend on how we get the lowest for the other. So 1, 2, 3. If we number the other way, it still ends up being 3. So we're going to put bromo first because of the alphabet, not because it's number 1. 1 bromo. 3 methyl. Squeezing in there. I'll try it again down here. 1 bromo. 3 methyl. Cyclobutane. Any questions? Cycloalkanes have conformations as well. Because of the ring, we can't get rotation around these bonds. And so they can't twist around. And so we end up with adjacent carbons being in the eclipsed conformation. There's no possibility for anything else. So you can't rotate this one because this is restricting it. But when you get to larger cycloalkanes, they're actually going to kind of pucker because that reduces strain. There's strain in these cyclic compounds because what is the bond angle that carbon likes to have? 109.5. And if it makes a square, what are the bond angles? 90 degrees. And so that doesn't make it real happy. And so what it does is it's going to kind of pucker. Do you see how it's doing that? It's not a flat square anymore. I can make it be flat, but it doesn't like that. It's going to pucker a little bit, and that's going to reduce some of the strain, and it also gives a little more space for the atoms that are attached to it. So we draw those like this. Here's the I'll use pickled banana, cyclobutane, and here's cyclopentane. And so they're going to pucker like that. When we get to cyclohexane, with 6, we'll notice that there are 2 different kinds, or 2 different orientations for the hydrogen atoms. There are some that are sticking straight up and down. These we call the axial hydrogens. And then there are some that are sticking straight out, the equatorial. The equator goes around the middle of the Earth, right? And so if you think of this as being around the middle of the Earth, the equatorial hydrogens are going around the middle. So these are equatorial, and these are up and down along the axis, the green ones. Cyclohexane makes this chair formation. You're like, how are they getting a chair out of that? Well, how do you get a hunter out of the constellation Orion, right? You have to use your imagination. So the blue is the carbon bonds. So here's 1, 2, 3, 4, 5, 6. So it's forming a chair. So the axial hydrogens are above and below the average plane, and the equatorial are approximately the same plane. And the chair can flip. So the axial and the equatorial carbons can trade places. Nope, that's only 5. I'm trying to make a model quickly here. I should have made it beforehand. I'm going to drop these on the floor. They bounce all over the place. Okay. Come on. Yeah, no, that's a boat. There we go. This is the chair. You gotta use your imagination. Here's the back of the chair, and the seat of the chair, and here's the front of the chair. Then we have these hydrogens. Some of them are sticking straight up. Oops, wrong bond. See those guys? They're straight up. And there's some that are straight down. That guy's missing. And then these guys are going out around the edge. And the chair can flip. See this green one down here? It's axial right now. If I flip the chair, now the green one is equatorial. And so the cyclohexane can flip, and the hydrogens that were equatorial become axial and back and forth. When we have larger substituents on here, like a methyl group, instead of just hydrogens, those larger groups are going to want to be in the the equatorial position because they have more space. When they're in the axial position, they're going to be too close to each other, and that's not preferred. So if we look at methyl cyclohexane, we see that 5% of it has the methyl in the axial position, and 95% has the methyl group in the equatorial position, because it's just got more space. It's like kids in a minivan. They would prefer to spread out. The bolt conformation is also possible when you flip both ends up. And if we look at this, why might you think that this is less stable than the chair? How close are these hydrogens? They're fighting close. They're really, really close. So it can make a boat. So it looks like a boat. This is the prow and the stern, or whatever they call them on boats. But it's not very stable.